This is similar to the example we did. We have a car slowing from 15 meters per second, and I give you, just for mental visualization, that's about 34 miles per hour. And it goes to a stop. If the 81 kilogram driver, and now we're going to talk about the force on the driver, not the car, is wearing a seatbelt, he'll stop with the car in 0.4 seconds. But if he's not wearing a seatbelt, it'll be about 0.08 seconds. And that doesn't seem like a big change. They're both less than half a second. But it will make a big change in the amount of force on a person's body. So we know that our mass is 81 kilograms. And our first velocity is 15 meters per second. And our second velocity is 0. We can immediately calculate our momentums. For the first momentum, we do 81 times 15, gives us 1,215 kilogram times meters per second. And we know that our second momentum is 0. We don't always have to be starting from a stop or coming to a stop, but it does make the math a lot easier. Our impulse momentum equation tells us that F delta t, and that just means a change in time, is equal to the change in momentum. So we know that for all of these, we can solve for force by finding the change in momentum divided by the change in time. So when we have a belt, I'm going to say with belt, and you know how I am, I like to label my work so that it makes sense for you when you're looking at it later. And with the belt, we know that time equals 0.4 seconds. And we know that our force is equal to P2, which is 1215, divided by 0.4 seconds. So our force, and if we're trying to put it into significant figures like we should, we get negative 3.0 times 10 to the third newtons. We have to put it into scientific notation because that's the only way to make this 0 significant, but not all the other ones. But we know that that really looks like 3,000 if we're not worrying about significant figures. And we're going to talk about without the belt. When the time is equal to 0.08, you can say our force is equal to, it's going to be the same change in momentum, but divided by a much smaller time. And we get about 15,000 newtons when we round to significant figures. And you can see for what looks like not a huge difference in the amount of time, we get 5 times more force. So you see all those things about like, oh, the seatbelt left the bruise, or we had this kind of damage. Well, that's with 3,000 newtons of force. It's a lot better than not wearing that seatbelt and getting 15,000 newtons of force. A lot of times we think about seatbelts as keeping us from launching out of the car. And they do that. But they're also made of a slightly stretchy material so that they give just a little bit in order to make it just a little bit more time. You still think that's less than a second. That's less than half a second. That's still not a lot of time, but it greatly reduces the amount of force on your body.